Hello friends, welcome to my channel. Let's have a look at problem 2420. Find all good indices. In this video, we are going to share a solution based on prefix and suffix counting. So in fact, the idea here is like that of the CDF in probability. And in the writing of the code, so we shall also see some flavor of dynamic programming. So for this problem, we are required to return an array of good indices sorted in increasing order. So roughly speaking, a good index is that there are key elements to the left and they are non-increasing, and there are key elements in the right, they are not decreasing. So in example 1, so the return is 2, 3. So for example, if we interpret index 2, so here is corresponding to index 2. So to the left, there are 2, 1, so they are decreasing. And to the right, there are 1, 3, so they are increasing. So 2 is a good index. So similarly, we can interpret the index 3. So this is actually the output for example 1. So for example 2, so k is 2 and the nums array has length 4. So in order that for an index, so there are 2 elements in both right and left. So the array should have length at least 2 times k plus 1, that is 5. So here the length is 4, so the return is empty. So the additional assumptions or constraints is on the range of elements and length of nums array and the range of k. So with that said, let's look at the idea. So the idea actually is the following are embodied by the following 3 items. So basically, we're going to use prefix sum to compute for each index the length of the longest non-increasing subarray ending at index I. And we are also going to use suffix sum to compute for each index I the length of the longest non-decreasing subarray starting from index I. So notice that in A, so it's ending at index I, and in B is starting from index I. So the item C is that, so with the information gathered from A, B, so checking the good index is actually a simple task. So here, before we write the code, let's look at one example. So this is example 1 actually. So we're going to initialize the prefix and suffix table. So here I'm going to use 0 initialization to fix the idea. So actually in the code, we can use 1 initialization, which is more convenient. So we're going to set prefix 0 and suffix n-1 to be 1. Then we're going to determine the prefix and suffix table. So for prefix, so we iterate from index I. For index I, from small to large or from left to right. So here is a condition or update rule. If nums I is no larger than nums I-1, in other words, the piece from I-1 to I is not increasing. So we are going to we are going to set prefix I to be 1 longer than prefix I-1, right? So otherwise, we're going to start over again. So prefix I will be 1. So you can interpret this by the meaning of prefix I. So similarly, we can set suffix. So we iterate for index I from large to small or from right to left. So here the condition is that if nums I is no larger than nums I plus 1, then it means that from I to I plus 1, so this piece is non-decreasing, right? So we can enlarge, right? So the prefix I will be prefix I plus 1 and plus 1. It means that starting from index I, the length is 1 longer than starting from I plus 1, and the non-decreasing property is kept. So otherwise, we're going to set the suffix to be 1. So here, let me do the change. So here should be suffix also here suffix. So with the above rules, so actually we can determine the prefix and suffix for this example. So then actually we can examine for each index. So if there are at least key elements to the left and to the right and maintain the monotonicity property. So for example at index 2, so here, right, then if we look at the prefix at index 1, so this is 2, and we look at the suffix at index 3, that is 3. So both 2 and 3 are no less than 2. It means 2 is a good index. So similarly, we can interpret index 3. So in general, at an index, if prefix I minus 1 is no less than k, it means there exists length k non-increasing subarray in the left. So similarly, if the suffix I plus 1 is no less than k, it means there exists length k non-decreasing subarray in the right. So such index is what we want. So with that said, let's look at the solution or the coding. So the coding actually is rather straightforward. So first I'm going to initialize the length of nums. So this is just for convenience. And then we are also going to set the prefix and the suffix table. So here I'm going to use one initialization. And then what we're going to do is to set the two tables. So for I in range 1 to n. So this is to set the prefix table. Then we're going to check if nums I is less than or equal to nums I minus 1. In other words, no larger. So if it's no larger, so the monotonicity non-increasing is kept. So we're going to do this. Prefix I equals prefix I minus 1 plus 1. So otherwise, the prefix I would be 1. So because we used one initialization, we do not need to do anything. So this is the set for prefix. Then for suffix, so we are going to iterate from right to left. Then we are going to start from n minus 1 minus 1. So that is n minus 2. So we're going to end at 0 and with step -1. So then if nums I is less than or equal to nums I plus 1. So in other words, the non-decreasing monotonicity is kept. So in this case, so suffix I would be suffix I plus 1 and plus 1. So here, because we use I plus 1, so we start from n minus 2. So above, because we use I minus 1, so we start from 1. So with that said, so we have basically done the set for prefix and suffix table. So this true for loop actually has some flavor of dynamic programming. So next we are going to prepare the result. So for preparing the result, so we can do an iteration. So for I in range, so because we need for each index, its left should have at least a key element. So we start from k, and also we need at least a key element to the right. So we end at n minus k. So in this case, so if we write range like this, so the ending index will be n minus k minus 1. So then we are going to check if prefix I minus 1 is no less than k and suffix I plus 1 is no less than k. If this is the case, index I will be a good index. So we are going to append it to result. So after this for loop, we can actually return the result. So this is a full solution format for this problem. So now let's do a special case check. Yeah, it passes example 1. Now let's do the generic case check. Yeah, it passes all the cases. So actually for this problem, so once we realize we can do the counting using prefix and suffix, then checking the good indices actually is a simple task. So with that said, I guess that's about it for this video. Thank you very much.